And our guests are going to describe for you and give you a little taste of what it was like on a day-to-day basis to struggle with some of these technical problems. And so we'll reserve the majority of our interview for that portion. But to begin with, I would like to have each of them introduce themselves and kind of give you some background as to how they came to be sitting here today telling us their story of the Apollo heat shield. So we will begin. Ken, we're going to ask you to begin. You're mic'd up, so all you do is just speak.
Well, thanks, Jerry. Nice to be with you, and thank you. My plans came today. I've been told by one of my children that I had better be careful with any equations or technology I put on the board. They're going to severely check it, so I'm going to have one equation on the board, a very simple one. You'll all be able to understand it. I'd like to say I'm so happy that my friend Ted Nishimoto came. Almost 60 years ago, we were in the same group together. Dr. Tony Capelli's not here, but otherwise we'd had the triad that actually worked on the heat shield, all working together with trying to solve these crazy equations that were coming along. We had no finite element analysis. We had no cloud. We had very little and computer wares, slide rules sometimes, but now we were going into things like Fortran translation, Fortran 2, Fortran 4. We had some programs that we could write in. So it was an interesting time. Getting started to go to school in engineering, I guess I look back at the greatest impact that I had as a teenager in high school was next door neighbors. Three of them had come out from Ohio to do graduate work at UCLA and SC. And they came out and they were next door neighbors, and I was taking trigonometry. And I remember clearly going over, with my problems, to have solved my trigonometry problems with these great bachelor's degrees, getting their master's, and I know they could solve my problem. Well, fortunately for me, they were wonderful because they did not tell me how to solve the problems. They did everything but they told me closely how I would go about solving the problem, but never telling me directly. So this was really an encouragement that if you can meet friends, if you can meet some people as you're growing up and getting inspiration to go into school for some reason, this is a wonderful thing you could do, is have a neighbor that could help you like that. So, went to New York, was going to go to Columbia. That failed. There was a real bad problem there. Came back out and came to North American Aviation. At the time of the Hound Dog, a missile, air-to-ground missile, which was a real flop. It was too expensive. It was worthless. They got rid of it just in time for the Apollo. In November of 1961, we got the contract, and things started. Took the lowest of 12 applications, lowest paid to take to go to North America. Why? Because my family was here and I enjoyed being in the Southland. But we started and we finally met together with you and Tony, and we had this problem. And it was quite a shock to my system. I don't know about you, Ted, but the first shock I had was looking at what NASA said what might just be our first encounter with trying to solve the problem of the heat shield coming back, the whole Apollo coming back with the astronauts safely into this kind of an environment. This was very disconcerting. I just got a degree, an undergraduate degree in aeronautical engineering. We're probably the fastest object I had studied was about 250 miles an hour, maybe an increase in 5 to 6 degrees in temperature on the surfaces. And we were told we're going to have to solve this problem. We're going to have to bring these men back safely with instruments like this. It was estimated it was going to come back through the atmosphere at 25,000 miles per hour. That's 36 thousand, something like that, 700 feet per second. And the temperatures at the spike temperatures, the stagnant point would be something like 5,000 degrees. 5,000 degrees using steel and aluminum and whatever to get back through the atmosphere. That was a very challenging, and I think I had a few nights that I didn't sleep very well, thinking how are we going to do this?
Before we get into the details of how you tackle that problem, I'd like to take a minute here and ask Ted to introduce himself. Ted, your background, you were here on site as one of the engineers. Actually, there's an aspect that Ted was sharing with me earlier that I'd like you to also share in your story. Ted was one of the rare individuals who worked on this site when we were building a nuclear reactor in Downey. The SNAP program. Ted.
Fat chance now.
Fat chance?
Yeah, after I graduated, University of Utah, I had an interview with Lockheed people. So I was coming down the coast.
Okay.
And they were going through these waves that we don't need anybody, but tomorrow we might. So you leave your phone number and keep on driving, because I've got a credit card that'll give me gas back home. So I came down to LA just to see LA. They tell you, driving from Santa Barbara into Rocketdyne, it's a great big pumpkin field from Topanga Boulevard over to whatever the other one was there, DeSoto. So, what the hell? Going to the front office, and here I am. Got anybody who'll talk to me? Well, he recommended I go talk to somebody over at the Atomics International. They were moving from this facility out to Canoga Park. I'd never worked on reactors. I was an architect student for 3 years, and then they booted me out for flunking a structures class.
So that qualified you to build an atomic reactor, right?
So I went back to the ME department, and life was so much easier over there. It's right or wrong. It isn't, I like this, I don't, and the prof's over there going, I don't like this, I don't like this. So it was nice and deterministic, and you knew what the heck to do. Engineering was easy. This is a piece of cake. In fact, I caught up with the other guys that had started in the other factor, I suppose, is AI was going through a boom going forward. They had Snap 10 and Snap 2 and Snap 4. They had 4 contracts, the AEC, and it was a chain of technology developments. The first one was relatively primitive. It's just thermocouples to make the electricity. Snap 2 had a liquid metal turbine, and Snap 4 was a secret of many secrets. But I was so fortunate to have started at that point, because I spent a lot of time waiting for my clearance to come through, which made me vulnerable to the boss sending me to places he didn't want to go. So I'm over at Rocketdyne, I don't know, computer for nothing, And then you go listen to the little lectures of how you do things. Yeah. And then a problem came up where it's a simple structural problem, right? I've got to invert a 6x6 to, and we were talking about it in, I guess, the lunchroom. Someone one of the things about, see, that was my first job from Thomas International. I never looked for another job from that point to retiring at Boeing. I come from North American to Northbury Downey, Rockwell, Boeing, whoever else got in the way, we absorbed them, or they absorbed us. And I retired from Boeing. I worked 50 years for this company.
Wow, 50 years, congratulations.
Yeah.
So, you two then, at some point in time, here at the Downey site, met up
Yeah.
to tackle this heat shield problem. How are we going
We're
to?
trying to think about what time that was, Ted, about 64, I believe. A friend by the name of Anthony Capelli, Dr. Capelli, had just come back from NYU. He'd been here for the master's. We got scholarship, complete pay to go back to NYU, and came back for this dusted PhD, and ready to tackle this problem. And the three of us are putting this triad, I mentioned, to work on this problem. He had written a paper about 59 or 60 on shells of revolution. And as you know, well, anyway, this getting started, this is the way I felt. This is about how much knowledge I had about this. And going at it, I thought maybe we'd take the airbag to zero and build on this.
Oh, pretty easy target to hit, though.
Right. Well, what was interesting, we soon found out, you managers did a great job putting all these little groups together. And there were hundreds here. We went from 5,000 to 35,000 in, 5 years, something like that, spread out. We couldn't get enough of these bungalows and the trailers.
We had trailers,
back-to-back trailers.
That's right.
On these premises.
We had desks in the aisleways.
Yeah. So, anyway, we're here, ready to work on this thing. You put together some very fine groups for us with which to work. Preliminary design, materials that are going to be used. The loads, there are loads of pressure loads and temperature loads, as you can see something like this. They had groups of pressures and a temperature group that would feed those things to us. We can plug them into our analysis. And so with these groups, these interactions, we worked back and forth with them and got inputs and gave them outputs. If we had a big pile of Fortran program results, and we were piling over and we found something, and we could go back to preliminary design. And so with this interaction of how this was going to work. But at the beginning, it was very, very difficult because what's it made out of? We know what the temperatures and pressures are going to be, but what's it going to be made out of? How are we going to put steel against 5,000 degrees of temperature? And I'll start from the bottom. I'll put the pressure. I'll put this pressure, Sagne pressure profile, roughly as to how they had it, but somewhere, and we'll go in this direction. I don't know if we can get any of these to work now. The direction of reentry. So it'd be on this top side here, and we'll put that hot spot here, or as you golfers, what do you call the golfers on a one wood? The sweet spot? The sweet spot, in this case, the hot spot. This is the hot spot of the Apollo, like this. And we're looking at something like 5K. 5K here.
That's 5,000.
5,000 degrees.
Fahrenheit.
5,000. And then we have a isothermal, iso meaning the same, thermal line, maybe coming across something like this. Let's say 4, okay? And maybe 3K back here, something like this. And this trails off into to the opposite side at about 1,500.
So if you want to go to the cool spot, you head to the back.
You'd head to the back. Now, it turns out there is some symmetry here. There is some symmetry. There's symmetry right here in that. There's some symmetry right here. In that if we can solve the analysis analysis on that symmetric line. For the worst case, which is in here with pressures and temperature, we probably have a pretty good solution. But we don't have anything that will do this at this time. We're looking at the papers, so they're in the journals. We look at programs, available structural analysis programs out there. There aren't any. We look at the universities, and they're creating in the 1960s, they're starting to create all these great papers on shells of revolution. But there's a real strange thing about this loading, isn't there? This is a shell. We're looking at the bottom half of this shell, which is really like looking at a good analogy is like looking at a bowling ball. And if you had a machete and you could slice off the top of a bowling ball, perfectly slice off, it would be a shell of revolution, wouldn't it? A shell of revolution, perfectly symmetrical shell of revolution, right? Ours has a radius, this shell, of about 175 inches. And so it sticks out like, you know, like a gun, an oil gun. And many of your items you find in stores and in pharmacies have shells of revolution that you assume that you've never even thought about it, that they're under pressure, but they're shells of revolution. They're very fine for pressure, by the way. And this is in the right direction. It's against the forces. If it was in the other direction, it would be very bad, but it's in the right direction. Okay, so let's do the same thing if we had another color for the pressures. The pressures, I don't know, they're going to be different. They're going to be different, but there will be a pressure. There will be an isopressures. These are the pressures and the pressures and the pressures. We have those. So those are the two loadings. What do we find unique about this situation? We have a shell of revolution that has unsymmetrical loading. A shell of revolution with unsymmetrical loading. And there are no programs out there to do that. There are no finite element programs yet. Today they would take this, spin 1,000 finite elements over this, put pressures at every little triangle, every little triangle, put pressures in every little triangle, describing structural stiffness at each of the little points, and solve it carte blanche with any kind of loading on it. Today they do the whole airplane. They contain finite elements of the whole airplane. But in those days we didn't, and so we had to think about how is this going to be solved.
What is happening is a surface of the command module is coming in through the atmosphere, and as this surface comes through, it is interacting with the air. So take your hands, put your hands together like this. And I want you just to do this. And as you rub that, you are creating something called friction. Now, as you apply more pressure, your hands are getting warmer. And the warmer they get, well, that can be a good thing, especially on a cold day. But if you happen to be coming through the atmosphere at 25,000 miles per hour, and you've only got this thin skin of metal between you and your bottom, you can see where we need to control and understand that friction and that heat, which is the analysis that Ken and Ted were doing.
As a matter of fact, one for deciding what kind of material this heat show is going to be made out of has to do with that removing of all of that tremendous energy that's going to be created in the surface. And here is a piece of a very important Apollo. I understand from Jerry that this is a portion of Apollo 4.
Apollo 4.
Apollo 4 was the first Apollo into space out of Earth orbit on the first Saturn V, a 7 billion pound thruster, and took it way, way on elliptical orbit, way out into cold space, and brought it back into the atmosphere, simulating the re-entry speed that's going to happen coming back from the moon. 25,000 miles per hour at 5,000 degrees. Well, it's spalled and ablated. And ablation is, I like the analogy of ablation to putting together a canister of ice going to the beach. And you put Cokes and your beer and everything with ice. And at the end of the day, the ice has melted, but the drinks are still cold. The ice has given up itself, the material itself, by latent heat. The latent heat has actually changed the product from ice into another form. Well, this is exactly what our ablating material on the heat shield is going to be. The underlying structural part, the part that Ted and I were working on for the analysis, is this part and underneath it. That has the structural strength. We would not rely on the structural strength of the ablating material because it's a plastic honeycomb structure that has no outer face. So it has very little flexural stiffness resistance. All this structural strength will be taken by this stainless steel honeycomb. It's also honeycomb. Both of these are honeycomb. This doesn't look like it, but it's had this ablating material gunned into each of these cells. 3/8 inch hexagon cells. There are 370,000 of them over the whole Apollo. And each one of these cells, each one has to be gunned by a machine, by a person on each one. Each cell has to be gunned and filled, and it looks like this. This is the gunning done back at the Lowell, Massachusetts, of a fellow gunning the ablating material into the hexagon plastic honeycomb. That's what it looked like. Every cell, one at a time. They have a production line here, showing them filling all of the cells. A very time-consuming process. They had to go to school for 2 weeks before learning how to do this. If there are any questions as we go along, be sure to raise your hand.
What exactly is the ablated material? What is it made of?
It is it's an epoxy formaldehyde resin, and it's very, very viscous. It is so viscous you can slap it against the board and turn it upside down, it's not going to go anywhere. It's that viscous. That's why it couldn't be poured in or spatulaed in or anything like that. It had to be gunned in with those guns, air guns, for every one of them. And to make sure that it was done correctly for the whole shield, after the shield was done that way, they had to x-ray it and make sure that the bonds all the way down to the ends were satisfactory. Putting on the honeycomb itself on the stainless steel was quite a feat also. There's a plastic vacuum bag type of operation, and all the seals of the honeycombs against the stainless steel had to be very, very intact. It's very well done.
Why the honeycomb shape? Why not a triangle or a square or circle?
It could have been other shapes, but
I'll answer it this way. What animal can you think of in the world that has used a hexagon to put eggs in? It's eggs or honey, bees, millions of years old. What shape do they use?
Hexagon.
And a hexagon, because of the strength and volume. Strength and volume. If you think of, well, volume, you just make it squares, right? Squares, all squares. But there's no strength in that. Bees making squared honeycombs they wouldn't last the season, would they? For some reason, it's a great question.
The concept that you've just described is something we call biomimicry. Much of the of the engineering and the technology that we have today came from us trying to solve problems like this by going to the greatest engineering problem solvers in the world, Mother Nature. Mother Nature is solving problems all the time. The honeybees solve structure problem with the hexagonal cell configuration. Now, if you ask the question, well, how do they do that? Well, how does that little tiny bird with that little tiny brain create these incredible nests of sticks and twigs and string and so forth? Biomimicry is an incredible tool for us as engineers to look to. And to answer your question specifically, why not a triangle and why not a hex? 5 is better than 3.
Does that answer the question?
Yes, sir.
Yeah.
I have a question. So you were using some sort of tool and you were injecting the material into the honeycomb. From all the models and everything I've seen, that's like a completely smooth surface. So was it cartridges or was it, well, there was like something, it was calibrated so it puts in like say 3 inches and then smooths it down and that's how you got the uniformity?
When it was gunned in, I showed you the picture of the gunning. It actually spills over. This is a typical gunner gunning the material in. A very, very viscous, so viscous that you can't put it in any other way. You have to have pressure behind it, and you pump each of these cells individually, and it sticks out, and it doesn't look very good, right? It's a reddish brown material, and it looks pretty bad, but it cures. And after heating and curing, it gets extremely hard, and they can grind it.
Can you pass that around?
So take a
Sure.
grinder.
Show
Oh,
that,
I'd be glad
because
to.
it's hard
Okay.
for
Oh,
us
yes.
to see from way back here.
You bet. Be glad to do that.
Like, okay, here, so this way.
You crazy guys.
Yeah, okay, yeah, because.
Go ahead, pass it around. You
Yeah,
bet.
because
Anything in your
unlike,
hat here, if you see anything that you'd like to see, we'll pass everything around. Be glad to. Okay. Now, so we're going to take a slice here through the center, about the most interesting center, because that's where we're thinking the maximum pressures and temperatures are going to be on that axis. You can see it spilling over to this side, spilling over that side, probably in this region. So we have the honeycomb, and let's put another. These are greatly exaggerated. And we'll put another one out here like this, and this is this end right here, right here. So you see it's thicker. It's thicker, so I'll bring it out here like this. Okay. This is the honeycomb. This is the honeycomb stainless steel. This is the honeycomb resin, plastic resin. Good bond, super bond. All the structural strength in the shell, stainless steel shell, and all the ablative material on the outside. And you can see here coming back with Apollo 4, how much was left over? How much was left over? And Jerry can tell us an experience about that.
So, again, in principle, the theory was, as the spacecraft enters the atmosphere and starts coming back in, there is something we call the angle of attack. Okay, the angle of attack, if you take a center line through the spacecraft, and now this is the atmosphere, so it's coming through. If I increase the angle of attack, which means I drop this surface down, this whole base heat shield is being exposed and is heating up with the friction that we saw as it comes down through the atmosphere. Now, we know it's going to heat up, and we know that the ablative material is going to help protect us for a while, but we have to time it carefully, because if we increase the angle of attack, we're gonna have the heat from this friction only on the surface for less amount of time, because it's going through the atmosphere quicker. So as it comes through the atmosphere, it gets hotter, but it doesn't last as long. So now, can I hurry up and get through there before it all wears away? That's the decision on the angle of attack. But there's another decision on the angle of attack. If the angle of attack is too high, well, I reduce the temperature. It's going to take longer to come through the atmosphere, but I have another problem. Even though the atmosphere, we think of the atmosphere as the air around us, at this altitude, at the very top of the atmosphere, a vehicle at that speed, aerodynamically coming through, if the angle of attack is too great, it could actually bounce off of the atmosphere and then continue to go out into space. So, no more heat problems, but bye, 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 bye. No more landing either. Okay? So, this issue of the angle of attack and all the dynamics that Ken are talking about, these are all problems that we're trying to solve. Now, it turns out that long after the Apollo program, the company here wanted to propose to NASA the ability to maybe take Apollo spacecraft that have even been flown, and as you can see in this section here, there's a lot of ablative heat shield left. We didn't burn hardly any of it off. So we proposed to NASA, why don't you take the old Apollo command modules, even the ones that have flown, and we make them lifeboats and put them into the space shuttle or on space station, so that in an emergency, crew members could use them to return to Earth. All we have to do is take that charred portion, that ablative portion, and cut it off, machine it off, grind it off. And now I got fresh new ablative material and I can go do another mission. So that piece you see there, with a little bit of rework, I could probably get at least 2 more flights out of it. So that was our proposal to NASA. Unfortunately, NASA doesn't like to buy used equipment. And the idea of using Apollo over again was not appealing to them. So the program never went on.
And there probably weren't any onboard measurements of exceeding the elastic limits anywhere either. And if it had been, of course, they would have to scrap it and start all over again anyhow. I've got another drawing I'd like to pass around to you. It shows you the corridor that Jerry was just talking about. Here's the space shuttle, and it shows you altitude versus the time for reentry. The question might be, I've always wondered how long, you know, when you hear that it's coming back from space, how long did it take for the Apollos to splash down? Turns out they were almost all the same. Almost all. The Apollo 11 was a little longer because they wanted to go over some clouds in the ocean, and so they increased that angle of degree that you were talking about and went another 30 seconds to that side. And Apollo 15 had only 2 parachutes, so it had 30 seconds on the short side. But it shows time versus the re-entry in seconds, and it shows also the stagnation point and the deceleration and the pressure as a function of height. For some reason, NASA chose 400,000 feet as the place to start. That's about 76 miles, almost 76 miles, as the amount of molecules now starting to hit it. And these curves probably came from the Arnold Engineering Development Complex in Tennessee, probably. It shows the value of the heat, the flux, the deceleration, and the pressure as a function of the height. I'll pass this around and you can check that out. Some of those numbers will stick with you. One of them is 25,000 kPAs pressure that we're going to use here in Apollo, test the Apollo. So anyway, this is how this was how it was built. The stainless steel was made at Ronca in Ohio. The ablative portion was made at Avco for Avcoat. That was in Lowell, Massachusetts. And these parts, the panels were being made here, but they were being sent all over the world, getting their new coverings, ablative materials, attachments, that sort of thing, and then brought back to Downey here to be assembled for the command module. Well, the problem is we have a shell of revolution for which we have a lot of analyses for, but we don't have any analyses as for a shell of revolution that's imposed by unsymmetrical loads. So what do? Well, Ted and I and Dr. Capelli wrote some papers using a program that we programmed right here, maybe 1,000 yards from here, in Fortran 4, that would predict these events in the shell itself. And the way that was done was, and this is a little technical, and my son will help me out here if I'm wrong in this, but there are equations of motion, there are equations of boundary conditions, there are equations that describe the characteristics inside of the shell. And it turns out that the stiffness, the thickness, one of the major elements of the stiffness parameter, which is D is equal to E, the Young's modulus, times I. Structural stiffness is equal to Young's modulus times the area moment of inertia. And this for pH 15.7 is 29 times 10 to the 6 psi. And I is calculated for a sandwich structure. I won't go through the details, but here's the typical position. We're saying this was one of the Kim millings that takes place that makes this stiffer, less stiff, less stiff, less stiff. And so it reaches a juncture like this and goes on. It reaches another juncture and goes on. We have another sheet down here. We have a honeycomb. And so you can calculate I for this kind of configuration. But it varies if we take a point here in the center, and say this is theta, and this is R. Any position on the shell, then its stiffness can be represented as a function of theta and R. And temperature will be in here, but we're not going to deal with temperature. But this is how structural stiffness varies any place that we're at. Now, if we're symmetric, if we expect the loads to be maximum on this plane of symmetry, then what we can do is expand this term in what's called Fourier series, a Fourier series. If you want to get an idea what Fourier series is all about, I highly recommend you doing this. Just go to Wikipedia and type in Fourier series. It's a magnificent explanation of what the Fourier series are. And that is expanding any function, two-dimensional function, as a sum of sines, some coefficient, and a sine and a cosine. But it turns out we have a plane of symmetry for the stiffness. We can do away with one of these. We can do away with one of these. But we can expand this function now anywhere on the shell. And this is used in the equations of motion, before the shell itself. I know that sounds a little confusing. But that's the way Ted and I did it.
The problem was back in the 60s, we didn't have machines big enough for the base of this heat shield. So we developed a new process. It was called chemical milling. So if you take some metals, certain metals, example, if you take aluminum and you stick it into a beaker of hydrochloric acid, the same kind of acid they pour in your swimming pool to keep the bugs out of it. If you put aluminum into a hydrochloric acid, it will dissolve. The hydrochloric acid eats the aluminum and takes it away. So in our lab, we said, wow, you know, if we could control that, we wouldn't have to mechanically machine these parts. And we did. We developed a process called chemical milling. We could take a piece of metal, we could mask it off in certain ways, we could dip it into a tank of acid or chemical, and it would eat off everything that wasn't covered. And if you could control the geometry of that and the timing, we could reduce weight, we could control dimensions, we could create a floor that had different thicknesses in it. Chemical milling became a wonderful process for the Saturn V hardware, for the Apollo hardware, and for other applications. As a matter of fact, I was telling the gentleman that, Ken and Ted, that I actually had the pleasure of mentoring and working with the original people who developed that process. And one of the gentlemen who developed it shortly afterwards decided to leave aerospace. And he started his own chemical milling company out in Orange County. Now, we all kidded him and we said, wait a minute, what are you doing? We're not going to be doing this forever, do you think? And there's not that many other spacecraft companies out there that want to have chemical milling done. He says, I don't need to. He said, I have the next 10 years working for NASCAR. All of the stock racers in the country were bringing their cars to him because they would take the shells, he would put them into his chemical milling tanks, and he would etch them down to 20,000 thick.
Wow.
He could reduce the weight of a car by 80%. So the concepts that you are seeing here, this engineering, the complexity, one of the most important issues to lunar exploration was this issue of solving how to return the crew safely and get them back through that atmosphere on the re-entry burn. Now, I have a question for them, both of you two. You were working and solving this problem, and 15 years later, I'm working with people like Ed and others here at this company on the shuttle program. We've got a new thermal protection problem. Our thermal protection system can't be ablative. It has to be reusable. And one of the issues that became very apparent at the beginning was we used little tiles, and if a tile fell off, that protective insulation was not there. The reentry heat would hit that metal floor. It would melt, and we had a condition we called burn through. As a matter of fact, that burn through condition is what actually happened to Columbia and spacecraft STS-107. So in the beginning, we had to figure out how do we solve that problem of burn through. Did you have a burn through problem or an issue similar on Apollo?
I've looked through all the references, post-Apollo structure, and I think the structure came through.
Yeah, no.
Always
it was
came through okay.
over-designed.
There was no burn-throughs. But Apollo, in the early days, it was considering using tiles. They were considering. And for that very, very reason, we can't let one of those come off
Too
with
risky.
5,000 degrees behind it.
Way
So it went to this all-inclusive shell of honeycomb, plastic honeycomb covering the stainless steel, which worked marvelously well, never came apart, never stalled or anything like that, so, yeah, it was very, very successful. All 17 of them.
I've been trying to think, your question about phenolic, what is the phenolic resin that they use? Another example of phenolic resin. Phenolic resin has been around for many years, and it's used in, a lot of times it's used as spacer or mounting blocks to insulate lines, like you have a hot steam line going through something, and you want to protect it from the heat. You would use a phenolic block, and you could fabricate it. It's epoxy based, so it's very effective in not just heat, but in strength for the volume. So think of, we've created and formulated a plastic as a resin that's very tough. Now, it turns out, it wasn't until many, many, many years later that in part of our use of these materials and experimenting with them, we found that phenolic resin compounds could actually be formed into fibers. You could actually make fibers out of it, much like you would a yarn or a twine. And so that phenolic type resin being formed into a fiber lets you now weave it into something like a cloth. Now, if I could create an epoxy-based resin cloth, like, and then you start thinking of how we were using fiberglass, you begin to realize how, gee, there were many more applications. And then towards, I believe it was the late 70s, 80s, early 80s, we discovered another formulation that we called Kevlar. And that same phenolic type resin that's in the heat shield of the Apollo became the bulletproof vest that our police officers and military wear today. Because they not only stop heat, if they're done correctly, they can stop a bullet.
Last questions?
One more question, and then we wrap up today.
Yes, sir.
I wanted to ask a quick question.
Yes.
You wanted to know how long it took to evolve this to make it happen.
Oh, excellent question. Ken,
Evolve what? Which
how long did it take you to solve this problem?
How long, how many years?
Kennedy's speech to
There you go. It was May of 1961
I
until
just happened to do this
March
calculation
of
the other night.
1972.
It turns out from Kennedy's speech until Neil putting his boot down on the moon was 2,967 days. 3,000, and it,
Good calculator.
yeah, 3,000 days. Or 10, just under 10 years.
Now we know.
But you'll be able to solve the next problem in a tenth of that time. Catherine.
No, Joe. He's been
Joe.
trying all morning.
Hello, Joe.
Hi. On the ablative process, was there any design consideration to making sure that it stayed even across the surface, both in terms of the aerodynamics and weight balancing for center of gravity, that stuff? Not lose it faster from here than there, so you don't have a problem?
Yes, there was some.
that's what the honeycomb's in there.
The honeycomb was in there, and that they.
So it doesn't just flow off.
Oh, you mean about the ablative portion of it?
That's what
The
it says.
ablative
Oh, the ablative
material,
portion.
if you're gonna lose it, did you have to try to make sure that it burned off at an even rate or a certain rate?
Yes,
To protect the
Right,
aerodynamics
right.
and the balance?
and that design of those honeycomb cells and the thickness, yes, that was all done for aerodynamic reasons.
So here's another calculation for you thermodynamically. You've got a stainless steel hexagonal tube that is filled with an extremely solid, viscous phenolic resin. But as the temperature goes up, and the reentry, the viscosity of that phenolic resin is going to go down, and it's going to liquefy. And depending upon the shape and the thermodynamics of the heat transfer into the metal to the surrounding cells, that's going to determine how fast that material ablates and comes out of the cell. And as it comes out of the cell, it's not there to hold the cell together anymore, so there might be some collapsing. So now you've changed the dynamics of the cell next to it, and the cell next to that, and the cell next to that. And with the plan, as Ken was describing, you begin to understand the complexity of how that ablation process had to be fairly well understood and controlled, but the only way you controlled it was by angle, pitch.
They flew these vehicles back like an airplane pilot. There were 10 rockets around this base here. There are 10 rockets and 2 on the top for yaw, roll, pitch.
If you come up and look at the heat shields, normally it's in the case over here. The only thing is, please do not touch it. The edges in it,
we're gonna put it
can you
back
put
in
it
the
back? Okay, we'll put it back. The reason is because that honeycomb core, those edges, when they get exposed, they're like razor blades. They're very, very sharp, and we don't want anybody getting injured. But we'll put it back in the case, and you can take a quick look at it, and you can look at that charring, because that's the material that burned, but it didn't ablate. So there's 2 processes going on. There's a charring, burning. Ablation is the actual action of it liquefying and the airflow blowing it away.
Jerry, I think I know his problem. I think I know why you asked the question. You saw Apollo 13?
Among others.
Have you seen Apollo 13? You remember the reentry? Did you see all that golden material as it came through the atmosphere right behind it?
The trail.
The trail of the bladed material burning off. Did you see that? That's highly overrated. Not that much came off.
But no, most of it came back and looked just like what you see there. What you see there is a prime specimen that helped us make sure that all future missions would be successful. And more importantly, that specimen, as I asked Ken and Ted, that validated the years of calculation and work that they put in to creating the right stuff. Thank you, gentlemen.